Every creator knows the promise of AI video tools: instant, effortless scale. But the reality usually looks like this. A machine strips away all the nuance, burying the actual video content under an avalanche of context-blind text. The standard cloud-based architecture is almost universally the same. Raw video goes in, a basic speech-to-text engine extracts a transcript, and that raw text is handed directly to a language model. This diagram shows the standard pipeline. The problem is what gets stripped away in that funnel. An LLM reading a transcript is blind to visuals, speaker identity, and pacing. Without context, the model guesses, spitting out a dozen generic variations requiring extensive human editing. Relying on text extraction alone severs the link between what is said and what is shown. It leaves the AI to describe the words while remaining blind to the visual context they inhabit. The alternative is to build a system that reads a video the way a human does. It extracts precise semantic meaning by analyzing the media across 4 distinct structural layers. Helm's deployment model is entirely local first. All media processing happens directly on your own hardware. Your unreleased footage and strategy never leave your machine. To achieve true machine understanding, Helm passes the video through 4 layers. First is audio diarization. Second is visual frame analysis. Third is chronological fusion. And fourth is the intelligence layer. The output of this pipeline is a complete publishing package. From a single source video, you get a structured set of titles, descriptions, and correctly cut short-form clips, formatted for 15 different platforms. Moving from cloud-based text extraction to local, multimodal processing is how technical creators retain absolute control over their media while automating the repackaging. The process starts the moment you drop a video file into the system. Background workers pick up the job and begin a parallel analysis of the sights and sounds. This animated timeline illustrates the first processing step. Layer 1 handles the audio. It maps exactly who is speaking at any given moment. It uses MLX Whisper for the transcription, paired with Pianote for speaker diarization. This locks timecodes down to the individual syllable. This word-level precision dictates how downstream clips are handled. Because the system knows the exact boundary of every syllable, it can enforce clean cuts that never interrupt a word mid-sentence. While the audio processes, Layer 2 analyzes the visuals. The system has to see what the audience sees to grasp the full context. It runs Qwen 2.5 visual language to generate detailed scene descriptions, and Apple Vision for optical character recognition. It reads the charts, title cards, and visual evidence exactly as they appear on screen. At this stage, you have 2 detailed streams of semantic data. But right now, they are isolated. To be useful to a language model, they have to share a single clock. The engineering challenge is that these audio and visual streams are just independent JSON arrays. An audio claim about a specific data point has no relational context to the chart shown 5 seconds later. This diagram illustrates Layer 3, the fusion layer. It physically merges the isolated audio and visual arrays onto a single master timeline. This creates a unified time-stamped scene log. Now, when a speaker makes a claim, it perfectly aligns with the supporting on-screen visual chart. That log is the input for Layer 4, the intelligence layer. Whether you use a local model or an API, the LLM ingests this unified JSON to act as the central logic engine. Because it has the full multimodal context, the LLM accurately scans the log for high-retention windows. It identifies narrative hooks and proposes thumbnail concepts based on what was actually shown. Feeding an LLM a time-stamped log allows the machine to write highly specific first drafts based on actual video comprehension. Extracting all that data requires serious compute power. The underlying software infrastructure is responsible for orchestrating this heavy processing locally. A typical cloud SaaS architecture relies on external dependencies like Redis or BullMQ to manage these tasks. Helm takes a lightweight approach designed for local machines. This diagram shows the software architecture. The entire system runs on a single PostgreSQL database, acting as the master queue. The software uses a custom SQL mechanism. Multiple local Python workers query the database simultaneously, using a skip-locked query to grab tasks without colliding. This creates an independent claim, run, acknowledge loop. It parallelizes the intensive machine learning rendering loads across Apple Silicon. This 150-line custom queue is what transforms a heavy theoretical ML pipeline into a high-performance desktop application. The user interface is built around the concept that partially ready is a first-class state. You can review and edit generated text while the heavy video rendering continues in the background. As you review those assets, the system enforces strict provenance. Every generated output must be traceable. The UI allows you to trace any generated asset back to its origin. You see the exact model, the prompt version, and the token inputs that produced it. The UI also enforces item potency, specifically within the state management of the shorts editor. Your clip plan is the absolute source of truth. Background ML workers only upsert data, meaning a background re-render will never overwrite your manual UI edits. Item-potent architecture and transparent provenance are structural requirements. They provide an audit trail for every asset, ensuring background processes never override manual adjustments. Escaping the cloud is not a free lunch. It is a highly calculated architectural trade-off with real consequences. The benefits are substantial. You pay 0 recurring subscription fees, your media is safe from harvesting, and the workflow is GDPR compliant. However, running a full multimodal machine learning pipeline places a very significant computational burden directly on your local hardware. You accept the maintenance costs. That means managing your own local Postgres instances and requiring capable Apple Silicon fleets to achieve fast render times. Channel Helm is an argument made in software. It provides the automation needed for scale while keeping the source media and the final editorial say on hardware you control.